I'm Ridmi Hesara and welcome back to my channel. In today's video, we will explore a well-known data structure and algorithm problem called the Tower of Hanoi. This puzzle is a perfect example to understand recursion, and we will also solve it using Java. Let's get started. What is Tower of Hanoi? The Tower of Hanoi is a classic puzzle that involves three rods and a number of disks of different sizes. All the disks start on one rod, arranged from largest at the bottom to the smallest at the top. The goal is to move all the disks to another rod following three simple rules. First one, you can move only one disk at a time. Next, you can only move the top disk of any rod. Last one is you cannot place a larger disk on top of a smaller one. The third rod acts as a helper during the moves. As simple as it sounds, the puzzle gets tricky as the number of disks increases. Why is Tower of Hanoi important? Now let's talk about why the Tower of Hanoi is so important when learning data structures and algorithms. First, it's a great example of recursion in action. The solution involves solving smaller versions of the same problem over and over, which is exactly what recursion is all about. Second, it follows the divide and conquer strategy where we break a big task like moving all the disks into smaller manageable steps that are easier to solve. Next, this problem is a very common question in coding interviews. Interviewers use it to test your understanding of recursion and how well you can break down a problem logically. It also helps you visualize the call stack. Each recursive call is added to memory, and only once the smaller steps are done, the calls started resolving. So, it's a great way to understand how the system handles recursive functions behind the scenes. Finally, it's excellent for improving your problem solving skills. You learn to think step by step, use logic, and follow a clear process. All very important skills in programming. Now, let's talk about how many moves it takes to solve the Tower of Hanoi puzzle. There is a simple formula 2 to the power of n minus 1, where n is the number of disks. So, for one disk, it's 1 move. For 2 disks, it's 3 moves. For 3 disks, it's 7 moves. For 4 disks, it's 15 moves. For 5 disks, it's 31 moves. This shows how the puzzle gets much more complex as we add more disks. It teaches us that even simple recursive problems can grow exponentially with input size. Now, let's see how the Tower of Hanoi puzzle actually plays out with 3 disks. This image shows the 7 steps required to solve the puzzle. Just like we discussed in the previous slide, using the formula 2 to the power n minus 1. You can see the 3 pegs labeled as S for source, A for auxiliary, and D for destination. In step 1, we move the smallest red disk from S to D. In step 2, we move the yellow disk from S to A. Then in step 3, The red disk goes from D to A on the top of the yellow one. Step 4 is the big move. The green disk goes from S to D. In step 5, we start moving the smaller disk again. The red disk goes from A to S. Then in step 6, the yellow disk moves from A to D. Finally, step 7 moves the red disk from S to D, completing the puzzle. You will notice the disk always follow the rules. Only one disk is moved at a time, and no larger disk is ever placed on a smaller one. This step-by-step view is a great way to visualize recursion and understand how each move is part of a bigger plan. Here is the pseudocode for the Tower of Hanoi. It uses a recursive procedure called Hanoi that takes four arguments: the number of disks n, the source peg, the auxiliary peg, and the destination peg. If there is only one disk, we move it directly from source to destination. Otherwise, we move n minus 1 disk from source to the auxiliary peg, move the last disk to the destination, then move the n minus 1 disk from auxiliary to destination. This structure helps us to solve the puzzle step by step using recursion. This is a simple Java program to solve Tower of Hanoi using recursion. The method is called solve Hanoi and it takes four parameters: the number of disks n, source, the starting rod, auxiliary, the helper rod, destination. If there is only one disk, we simply print the move from source to destination. Otherwise, we follow these three steps recursively. First one is move n minus 1 disk from source to auxiliary using destination as a temporary helper. Next one is move the last, it means largest disk from source to destination. Last one is move the n minus 1 disk from auxiliary to destination using source as a temporary helper. This recursive structure mirrors the logic in our pseudocode and helps solve the puzzle in the most efficient way. Here is what output looks when we run the program for 3 disks. Move disk 1 from A to C, move disk 2 from A to B, move disk 1 from C to B, move disk 3 from A to C, move disk 1 from B to A, move disk 2 from B to C, and then move disk 1 from A to C. Each of these steps follows the puzzle's rules. Only one disk is moved at a time. No larger disk is placed on top of a smaller one. This output clearly shows how recursion works step by step to move all the disks from source to the destination rod using the auxiliary rod as a helper. Let's wrap things up with some key takeaways. First, Tower of Hanoi is a perfect example of recursion, where we solve a big problem by solving smaller parts of it. It uses the divide and conquer strategy, breaking things down into manageable steps. The time complexity is zero, which means it grows really fast as we add more disks. It's a great way to develop problem solving and logical thinking, especially when learning DSA. And finally, It helps us visualize how recursive functions are executed using the call step. Each function wait until next one finishes. So, this is all for this video. Thank you for watching. If you found this video helpful, give it a thumbs up and subscribe to the channel for more DSA content. In the next video, we will explore tree representation. So, stay tuned. And if you have any questions, feel free to drop them in the comments below. Bye bye.